In this video, we are going to learn how to improve signals which look like this, how to improve them to make them look like this. And it's not very difficult. There are just three things what we are going to change in our design, and this is what will happen. My name is Robert Feranek, I'm from FedDevel Academy, and I really hope you will find this video useful. First, we are going to have a look at the circuit what we are going to use in this simulation. And the circuit, it looks very simple. It is very simple, but it is something what almost everyone is using in their PCBs. And once you understand how to connect and how to route this simple circuit correctly, it can help you to do your layout better. So when we have a look at the schematic, what we are going to use in this video, there are actually two simple circuits. In this first circuit, there is a connection between one output to multiple inputs. And in this second circuit, there is connection between only one output to one input. These chips, what we can see here in the schematic, they are just very simple buffers, these SN74 LVC buffers, so something what you may have on your PCB. And the difference between these two circuits is that here we are going to run 10 megahertz signal between this output and these inputs. And down here on this other circuit, we are not going to run any signal. We will just have a look. What kind of noise is going to be generated from this 10 megahertz signal on this connection between this output and this input? When we have a look on the PCB, this is what I created. Wow! The most complicated PCB I have ever done. No, I'm just kidding. It is very simple PCB, but still you can get like very bad signal if the schematic is not done properly and if the layout is not done properly. So again, when we have a look on this simple PCB, this is something, or these are the kind of connections what almost everyone will have in their PCBs. For example, this is a connection between one output and multiple inputs. So when you are routing one output, you need to split the track and route it to different chips. And also what we can see here, this is the place where on your PCB, for example, you need to route signals very close to each other. So here we are going to have a look how much noise the 10 megahertz signal, which is going to run through this track, how much noise or how much crosstalk it is going to generate on this other signal. And if this simple circuit, if this simple layout is not done properly, then this is what you will get. Very noisy signals. Can you guess what is what? So these green and yellow signals, these are measured on the inputs of these buffers. So they are measured here and here. And the blue signal, which is here, this is the signal which is measured on the input of this buffer here. So it is measured here. Okay, and all this noise what is here on this blue signal, it is generated from the 10 megahertz signal running through this track which is here. Wow! Notice how big the noise is, how low this goes, and how high this goes. If you have a look into datasheet of this gate, and when you check the levels, input levels for this buffer, you may find out that actually this high noise, it can change the levels of the output of the buffer. So we really don't want to have this kind of signals running through our PCB. And it is very simple how we can fix this. It is very simple how we can change this kind of signal to this. I was surprised actually when I was doing this simulation how big difference these three things, what we are going to change, how big difference they can make. And I'm really curious if you know what are these three things, what we are going to change in our schematic and in our PCB to have, instead of this signal, to get this kind of signal. Do you know? Tell me what we are going to change. You will see what these three things are. I printed the PCB, so you get the idea how small it is, because the dimensions are important. And also you can find the dimensions here in the PCB, okay, to give you an idea how long these tracks are. So 2000 mils between these 2 points, or 50 millimeters, and distance between this point and this one is 800 mils, 20 millimeters, and distance between this point and this buffer is around 1600 mils, or 40 millimeters. For simulation, we are going to use Cadence System Analysis, Sigrity Topology Explorer. I'm going to use this Topology Explorer license, and I'm going to open the project what I have already prepared. Let's have a look what we can see here on this picture. And I would like to talk a little bit about this because it is simple to set up, and once you understand how you can simulate your PCBs, it can help you when you will be designing your boards. So in this picture, you can see we are using 2 output buffers. We are using 3 input buffers, and then there are some elements which are describing the PCB. So when we have a look on our PCB, these are the 2 output buffers. These are the 3 input buffers. And this element which is here is describing the part of our PCB where 2 tracks are routed close to each other. So it is basically this part of our PCB. And these 2 elements which are here, they are describing the branches which are connecting the input 1 buffer and input 2 buffer. So in our PCB, it is this branch which is here and this branch which is here. Okay, so these 2 branches are these 2 elements here. To simulate the output in our circuit, I use this transmitter IBIS module. That's what you can see here. And everything what I did, I just loaded the IBIS model of the buffer. Then I selected the specific component what we are using, this DSF component. I set up the pin mapping, and that's everything. For input, very similar. I use this receiver IBIS element. Then I set the IBIS model for this element. I selected specific component and set the pin mapping. To specify our PCB, I use this trace element, or they call it block, okay, trace block. And I'm going to show you how you can set it up. So click here, trace editor, click on this new one. And in our simulation, we would like to use trace with 12 mils. So we are going to have 12 mil tracks in our simulation, 1.4 trace thickness. And initially we are going to simulate 2-layer PCB. So what is going to be substrate height? What is the standard height for 2-layer PCB? 63 mils. Okay, so this is basically how you specify your PCB in this simulation. I'm going to delete this, and we can have a closer look what I set up here. Let's go back to our PCB, and we are going to check this branch. The length is 800 mils. It is the branch between buff input 1 and this place where the track splits. So in our simulation, it is basically this element or this block. When we have a look at the properties, you can see the length is 800 mils. We are using 12 mil trace, and we are using 2-layer PCB. The second branch is this one. The length is 1600 mils. When we go into simulation, it is this block, 1600 mils, and again 12 mil trace on 2-layer PCB. This one, this is the block which specifies the traces, two traces routed close to each other. So we need to specify the length, and also we need to specify the distance between the traces. So 2000 mils, when we open properties of this, length is 2000 mils, and you can see there are two traces. Both traces, they have width 12 mils, and the space between these two traces is also 12 mils, okay? So this is the one trace, 12 mils, then there is space 12 mils, and this is the second trace, 12 mils. The distance between the top layer and the reference plane, which is on the bottom layer, is again the 63 mils, which we use for the 2-layer PCB. At this picture, you can also see we have connected everything together. So now you should fully understand what we have here, okay? We connected the outputs of the buffers to this block with two traces running in parallel. That's what we can see here. Then at the end of this parallel block, there is this input, which is called victim input. That's exactly what is connected here to the end of this block. And also at the end of this block with two traces, we split them and we connected the individual branches to the input 1 and input 2. So these two connections which are here are exactly these two connections, what we can see here. To specify the signals which we would like to run through these traces, we are going to use these setup analysis options. That's basically what we can see down here. So for the buff output, for this output, we would like to set this output to be 5 volts. We do it here because the models, the IBIS models, they are for different types of outputs, 1.8 volt, 2.5, 3.3, and 5 volts. We would like to run 5 volt simulation, so I'm going to select 5 volts. Then we would like to use this pattern. It is very simple pattern, just 0, 1, 0, 1, 0, 1. And here you can set the frequency for our signal. You don't set the frequency directly, you need to set it based on this data rate, which is in gigabits per second. So usually the data rate is double of the frequency, and for 10 megahertz signal, we simply just need to use here this value 0.02. For the victim output, again, we would like to use the 5-volt buffer, 5-volt output, but we are not going to run any signal from this victim output. We are going to just keep it set to 0. For the inputs, which are here, we need to only set the input type. So the input 1 is set to 5 volts. This second buffer is also set to 5 volts, and this victim buffer is also set as an input for 5 volts. And we are ready to simulate our circuit. So I'm going press start transient analysis. We need to wait a little bit. And here it is. These are the results from our simulation. Notice, okay, the yellow color is for buff input 1. So the yellow color is what we measure here. The green color is buff input 2. So the green color is what we measure here. And the blue color is victim in. That's the signal which is measured here. Before we continue, I would like to show you how bad actually this signal is. So what we are going to do, we are going to add 2 markers. Right click, marker. I'm going to call the first one like threshold high. And when we go into datasheet of our buffer, the value what we are interested to see is here. So positive going input threshold voltage, it means when the voltage will increase about this value, then the buffer will register the input signal as high. And for a 5-volt buffer, the value is somewhere between 2.19 and 2.65 volt. Let's use 2.19. So I'm going back to our graph and I will put here 2.19 at. So basically, when we have 0, then anything about this line which is here will be then registered by the buffer as high. And in this place and also in this place, you can see that this noise is higher than the threshold for high, and in some cases the buffer may register these peaks as high on the input of this buffer, and that should not be high because we are not sending high from this victim out. We are only sending 0 level, so here should be always 0. But because the noise is so high here, sometimes the buffer may register that there is actually high on the input. Very similar for threshold low. So I'm going to add another marker, threshold low. When we go back to datasheet, negative going input threshold voltage. Again, there is no exactly 5 volt. It is somewhere between like, I don't know, 1.97 to 2.4. Let's use 2.4. I'm going to put here 2.4 at. And basically, any value going from high to low, which is lower than this line in this place, what we can see here, the buffer may register that there is actually low value. Okay, so you can see this noise is so high that it can like influence or damage the signal which you are transferring through our PCB. And now we are going to have a look how we could improve this. The first improvement, what I'm going to do, I'm going to increase the length of this branch. So basically, I'm going to make the length of this branch exactly same as the length of this branch. It is called balanced topology. The length of this one is 1600 mils. So I'm going to edit length of this one and I'm going to change it from 800 to 1600. The second improvement, what I'm going to do, I'm going to add series termination resistor. So I go down here, I'm going to add series termination resistor and I'm going to use value like 33 ohm. The last change, what I'm going to do is I'm going to change the stack up. I'm going to edit this and instead of 63 mils, I'm going to change this to 7. And I will do it for all these blocks. Change this to 7 and also change this to 7. We are ready to run our simulation again and watch the difference. I'm going to press Start Transient Analysis and wow! Can you see the difference? Wow! And now I have got curious. I wanted to know how each change in the PCB influence this signal. So what I did, I reran all the kind of combinations of these changes and I simulated everything and then I took screenshots from the results. So next I would like to show you what happened with this bad signal, what happened when we did the changes on our PCB. This is the original bad signal, and if we would only adjust the length of the branches, this is what would change. Okay, in the background you can see the original signal. So this is the difference. If you would only change the PCB, this is what would happen. Okay, so from this signal, if you change only PCB stack up, this is what would happen. Then if you would only add series termination resistor, this is what would happen. Okay, so this is the original signal and this is the signal with 33 ohm termination resistor. If we would like to adjust the stack up and also if we would do the length matching of the branches, this is what would be the difference. Okay, if we would use series termination resistor and if we would use the proper stack up, this is what would happen. And if we would use the series termination resistor and only do the length matching of the branches on the original 2-layer stack up, this is what the result would look like. And this is the final improvement when all the three things are applied all at once. The series termination resistor, the length matching, and also the PCB stack up. There are two very interesting things. Watch this. So if we enable only 33 ohm series termination resistor, this is what we will get. And if we compare it with this situation, when we enabled the 33 ohm resistor and also we did the length matching of the branches, this is what has changed. See? So basically, the length matching the branches removed all this ringing which is here. Even when we use the 33 ohm resistor and when we use a proper improved stack up, you can see it helps, but we still see the ringing. So definitely the length matching of the branches will help to remove this ringing. That's why we did the length matching of the branches, to remove this. The second thing what I would like to point out is this. Notice how much the crosstalk was lowered when we improved our PCB stack up. So this is the original crosstalk and this is the new stack up. When the ground plane or reference plane is much closer under the signals. Do you know what we did when we changed the stack up? We have not only brought the ground plane closer under the tracks, but we also changed the impedance of the tracks. And when you have a look, I improved the impedance on the tracks to be, you can guess, 50 ohms. Okay, so when I press this button, which is here, it calculates the impedance of the track based on this stack up, what we have here, and based on the dimensions of the track. And you can see our tracks are now 50 ohm impedance. And this is also the reason why I use the 33 ohm resistor. I don't know the exact impedance of this output of the buffer, but these buffers, they usually have low impedance output. So when we add this 30 ohm resistor here, we kind of meet the 50 ohm impedance of this output, and that helps to improve the signal, because then output of the buffer is 50 ohms and the signal travels through the tracks with 50 ohm impedance. It means we improve the path where this signal travels, and that's why the signal looks much better in our simulations. Notice we have not done anything to meet input impedance of these buffers. And don't forget, this impedance of these buffers, input impedance of buffers, is usually very high impedance. So for the signal, it looks like at the end of these tracks there is nothing connected, or they are not connected. But still, even if we didn't meet this impedance on the inputs of these buffers, we are still able to get very nice high quality signal. This is very interesting because many buffers and many chips, they are not really specifically designed to meet 50 ohm impedance. But as you can see, it still can work very well. For example, if the impedance of the output buffer is very low, you can add a series termination resistor. Usually they are 22 ohm or 33 ohm series termination resistors, and this can help a lot. And not putting any special termination on the input of these input buffers, it's nothing really wrong, as I said, and as you can see, we still can get really good high quality signal. Basically, it can help a lot if you can meet impedance on at least one side of your track. Why? Because, For example, if you do not meet impedance on both sides or both ends of your track, what is going to happen? You send a signal through your track, it will arrive at the end of the track, and because the impedance at the end of the track is not matched properly, there will be reflection. And this reflection will travel back through your track. And because the other end of your track doesn't have proper impedance matching, what is going to happen? This reflection will reflect again. Okay? And this reflection will travel from one side of your track to the other one like this until it disappears. However, if at least one side of your track is properly matched, what is going to happen? Your signal will travel once it arrives at the end of the track, which is not properly, which doesn't have proper impedance matching. There will be reflection. This reflection will travel back through your signal, but when it arrives at the end of the track which has proper impedance matching, this reflection will disappear. There will be no reflection. So basically in this case, you will have like one reflection, but then it is gone. And this is why it helps a lot. And that's what I believe is happening in our case. So basically, this side of our track is some kind of impedance matched. And even if there would be reflection at the end of this track, where this high impedance of buffer input is, then this reflection will disappear here at this end of this, where this output buffer is located. There is something else what I would like to show you in this video, and it's about the length of these tracks. So what I'm going to do, I'm going to remove all our improvements. So I'm going to delete this resistor. I'm going to connect this back, and I'm going to use the two-layer PCB again. But instead of using these very long tracks, we are going to make them shorter. So I'm going to put here like 8 mils. On this other one, I'm going to change the stack up again to 63. Length will be 16 mils. And here, I'm going to change the stack up 63 and change this length to 20 mils. So what do you think, what is going to happen now? Is the result going to be still as bad as we can see here, or something is going to change? Don't forget, everything is exactly same as for our previous simulation, which was really, really bad. Only what we change are these lengths. So have a look at the results. I'm going to start the simulation. Miracle! Even with no series termination resistor, with two-layer PCB, not impedance matching, no 50 ohm routing, we are getting perfect signal. How is this possible? The thing is, there is specific length of your track when you some kind of need to start worry about all this noise, what we were talking about in this video. So if your tracks are super short, then you will always get like very nice signals. The question is, how long is the shortest track in your case when you need to start worry about all this noise, all these reflections and crosstalk? So Basically, your question may be, how did I come up with these numbers for our PCB, what I have here? What do you think? What I did, I measured the edge of our output signal. I'm going to disable all these results and enable the output from our buffer. Right click, measure rise and fall time of the output from the buffer between 0 to 5 volts, 10 to 90%. And you can see the rise time for our rising edge is around 600 picoseconds, and the fall time for our falling edge is around 500 picoseconds. Then I took a calculator. I put the 500 picoseconds here, so 0.000, that's milli, 000 micro, 000 nano, 5. So this is 500 picoseconds. And when we change this to frequency, we will get 2 gigahertz. When we search for a wavelength of 2 gigahertz, you can find this kind of calculator. I will put here 2 gigahertz into centimeters, and the length is 15 centimeters. When you change 15 centimeters to mils, you will get 6,000 mils. And this is 6,000 mils, or 15 centimeters, and this is our circuit. Notice our circuit, or the length in our circuit, is getting close to the length of the wave, which we calculated based on the rise time. And this is important. There are all the kind of rules of thumb which can help you to decide if or how critical the length of your signal is. I read it's like 1/10 of the wavelength or 1/12 of the length wave. I don't know exactly, but I can give you an idea how it looks in this simulation. So let's say we are going to increase the length of all these traces. I'm going to change this to 200. I'm going to change this to 80. And I will change this one to 160. And when we run this simulation now, the results are not going to be as nice as we had before. See? And if we even increase the length, let's say we will multiply this by 2, 400, 160, and 320, oops, like this. This is how the result is going to look. This is just to give you an idea how the length and the rise time of the edge influence the quality of the signals on your PCB. When I was talking to a friend of mine about these simulations and about these results, he pointed out two very interesting things. First, he asked me if this output signal is not going to be square, like with right angles. And I believe the output signal, what we see coming out of this buffer, it is based on the IBIS model. So the output signal, the rising edge and falling edge of the signal what we see in this simulation going out of this buffer, it is exactly what you should measure on your real board. And if you use different kind of buffer, then the rising and falling edge of the signal would be different. Okay, so if you would use different buffer with slower rising and falling edges, then maybe you can use even longer tracks on your PCB and you will not have any problems. The second thing what he pointed out was like, but I don't really see this kind of signal on my scope, or will I measure this on my scope? And this is very good point, because you may need to have very expensive scope to be actually able to measure something like this. If you use a cheap scope, then what you will see, it may look completely different, it may be completely wrong, and it may not show you what is really happening on your PCB. Okay? So don't forget, your scope may not be showing you what is really happening on your signals. Why your scope may not show this correctly? Do you know? One of the biggest reasons is that to show this kind of signal, your scope would need to have very high sampling rate, and this is usually possible only in very expensive scopes. Also, in this video, I intentionally used 10 MHz signal because I wanted to show you that you don't need to have very high-speed signals and you still can get this kind of problems, this kind of noise. Even if this signal is slower than 10 MHz, you still can have this kind of noise, because, as you could see, what is important is the rising and falling edge, how fast the buffer what you are using in your circuit is, because the type of this buffer, it will specify the rising and falling edge of the signal. So even for even for slower signals, you still can have this kind of high noise in your boards. And that's everything for today's video. Hooray! I didn't want to make so long video, but there was a lot of interesting stuff what we can see from this simulation. So yeah, I made it a little bit longer than what I was expecting at the beginning. Leave comments, okay? Let me know what do you think. What do you think about this simulation? What do you think about the results? What do you think about what we can learn from this simulation? And I'm curious. I'm curious to know if you found this interesting and useful. If you like this video, don't forget press a like button. Also, don't forget to subscribe, so it helps me to create new videos. I would like to thank you very much for watching, and see you next time. Bye.